All right, good afternoon, everybody. My project title is the structural analysis of foliations within the southeastern New England Avalon terrain within the states of Massachusetts, Connecticut, and Rhode Island. My name is Ruben Calle. I just graduated from North Carolina State University, and this is my project. To start off, I want to acknowledge that this project is an extension of a 2019 project conducted by RESESS intern Janice Pipkin under Dr. Yvette Kuiper as well. She worked on the Neshoba Putnam terrain and the Merrimack Belt directly west of the Avalon terrain. The Avalon terrain is here in orange. And the purpose of my study is to investigate the role of the late Paleozoic alligator orogeny on the Avalon terrain. A little bit of background information. Focusing on the diagram in the middle, we see that ancestral North America is on the left, and we have Africa on the right, with the Avalonian slab here in the middle in green. So basically, this is analogous to the diagram on the right, D, in late Pennsylvania, where we have a lot of fold belts forming in the formation of the Appalachian Mountains and the supercontinent Pangaea. So the big picture of this is that the alligator orogeny is a joining of two continents to form the supercontinent Pangaea. And the Avalon terrain is composed of multiple fault-bounded Neoproterozoic volcanic sedimentary belts and accompanying plutonic rocks, mostly tied to juvenile island arcs. And these island arcs are displayed throughout A through C, in the diagram to the right. In A, we have the Avalonian island arc coming in and closing the western Pacific Ocean and coming in contact with the North American plate. And then in B, we have the closing of the eastern Pacific Ocean with the Proto-African plate coming in as a volcanic island arc as well, and coming in and hitting the North American plate. And in C, we have the formation of the supercontinent with a bunch of volcanism occurring and plutonic rocks coming up to the surface. For the West Trending lineaments anomalies, this is a figure on the right from Allison Severson from her PhD dissertation in 2020 with the Colorado School of Mines. We see West Trending lineaments labeled A through H. And we're going to focus on lineament E in red with the alligator in front. The alligator in front separates predominantly Acadian metamorphism to the north from alligator metamorphism to the south in the states of Massachusetts, Connecticut, and Rhode Island. A little bit of a background for aeromagnetic anomalies. A magnetic anomaly is a small scale irregularity in Earth's magnetic field and could be caused by mineral deposits. Gravity anomalies, as seen in B, are due to unusual concentrations of mass in a region. Depicted in red, we see elevated areas, which are depicted in red. We have positive gravity anomalies, which can be depicted by elevated areas or mountainous environments. Depicted in blue, we have negative gravity anomalies, which could be described as depressions in land masses, such as valleys, or if we're talking about more oceanic environments, it could be considered oceanic trenches. As for my methods of digitization of measurement locations, I predominantly use GIS files or PDFs of bedrock geologic quadrangle maps. GIS files were much more easy to work with because of you just need to upload them onto ArcGIS Pro, and you could cut out exactly what you wanted and what you didn't need, and you would simply just change the symbology to make it look more appealing, like a foliation line. As for the PDFs, I used GMDE whenever I only had PDFs of geologic maps. And in GMDE, I manually digitized quadrangle maps. For example, here we have the Milford Quadrangle located in Massachusetts, depicted here by the yellow square and the Avalon terrain. And here are blown up images of these foliation data that I compiled. So there's approximately 400 to 500 foliation points that I had to manually digitize, which took a decent amount of time, but the work got done. And this was done on GMDE, and Orient was used as a stereographic projection software where I developed stereo nets. For data compilation, we predominantly looked at strike and dip measurements. A little bit of structural geology for you. A dip is an angle in degrees between a horizontal plane and a declining plane. And the angle of dip provides information about the movement of the magnetic field of the Earth. The strike is a compass direction of a horizontal line in a declining plane. On the right, this is a map I created on ArcGIS Pro depicting foliation data with a gradient scale from 0 to 90 degrees for dip angles. The majority of our data is comprised of dip angles lower than 45 degrees and some of the steeper angles reach 90 degrees, which are heavily pocketed within the southern area of our area of study and the northern portion as well. These are my map results. I compiled approximately 9,000 foliation points, digitized them, and then analyzed them. 39% are northwest dipping, which means they strike between 180 and 270 degrees. 46 are northeast dipping, meaning they strike between 270 and 360 degrees. On the bottom left, we have an image kind of describing how to calculate dip direction according to strike direction or the angle of strike. Here on the left, we have a legend depicting the 8 octants I made from 0 to 45, 45 to 90, depicting strike direction. And I had 9 domains that were created as well, which are divided based on general trends and dip direction. And these 9 domains were created on ArcGIS Pro using the Tyson Polygon geoprocessing tool. These are the 9 domains, stereo nets of the domains that I created. On the far right, we see the clustered and spread out chart. So where we see red on the stereo nets is where the majority of our data is concentrated. As we transition to the blue area, it's where we get more variety and more spread out clusters of data. So the tighter the bullseye, the more clustered the data is. And the more, for example, on 2, the more variable it is, you see more blue. This is a large scale image of my domains in correspondence to the stereo nets as well. I took out all the strike and dip measurements to make it look a little bit more cleaner. And I also included the Allegheny front, which I mentioned earlier, which divides Akkadian from Allegheny metamorphism. So we see here in domains 1 and 2 that we see in domain 1 right above the Allegheny front that there is northwest trending foliations within this area. And then transitioning to 2, right at the border of the Allegheny front, it begins to shift a little bit. And as we transition down, we see that we see it move towards more to the northeast. As well, we see in domain 4 and domain 3, opposite facing dip directions. This could indicate a potential fault line right across, right down the Rhode Island and Connecticut border. And these are the other domains that I've created. Here we have the Willimantic Dome, which is a regional deformation caused by a thrust fault. And it is a shallow amplitude gneiss fault. So for my conclusions and data interpretation, the dominant dip direction of this portion of the Avalon terrain is northeast. Based on foliation orientations on state maps and preliminary work from the 2019 projects connected by Janice Pipkin, we expected there to be largely northeast striking, meaning northwest dipping foliations. The northernmost domains display northwest dip directions as described earlier. These domains are located above the Allegheny front or at the Allegheny front. The Allegheny orogeny may have overprinted and deformed these previous metamorphisms caused by the Akkadian orogeny, which may have altered the dip direction below the front. Areas that display opposite dip directions, examples were 3 and 4, may reflect unknown faults in the area that could definitely be studied at a later date. The research area is on the unceded lands of the Pawtucket, Pokanoket, Narragansett, Mohegan, and Quinnipiac peoples. I ask you to join me in acknowledging these communities, their elders, both past and present, as well as future generations. We also acknowledge that this region was built upon exclusions and erasures of many indigenous peoples. This acknowledgement demonstrates a commitment to beginning a process of working to dismantle the ongoing legacies of settler colonialism. And thank you to the NSF for providing the funding, and this was a great opportunity for me. Thank you to Dr. Kuiper as well, and my mentor, my communications mentor, Jordan Watchholtz, for all of his guidance, good tips, and some ArcGIS tips. Thank you.
Okay, and we will now open the floor for questions. So again, you can unmute yourself and raise your hand so you show up at the top, or you can type it into the chat and we will read it for you. Lon has a question.
So Ruben, thanks. I enjoyed that. So you talked about some of the specific local consequences or interpretations of your data. Can you put it into any kind of a broader tectonic context of what did you learn about the Akkadian orogeny from your work?
Well, our work predominantly was focused on the Alleghenian orogeny. What do you mean, the Alleghenian, or do you want to talk a little bit about the Akkadian?
Well, either one. Go ahead. And I mean, I'm a tectonics guy, so
Right.
walk me through. It's a fascinating set of orogenies that you've got there, and I know a little bit about it, but not a lot. And so, just educate me on what we know from your work that we didn't know before.
It's a great question. Well, what I learned a lot during this project was this transition model on the right. I didn't know about all these microcontinents that came in and basically as volcanic island arcs and came into the to form like what we know today as the Appalachian Mountains. So I think for me, all this volcanic activity is pretty neat. And referring back to your question, like I really do not know. I had to put my words into the context right now to answer that question.
Fair enough. Thank you very much.
Absolutely.
Appreciate it.